this video, we're going to talk about Chapter 6, Section 5, which is the midsegment theorem. And we're going to talk about how the midsegments of a triangle are related to the sides of a triangle. So to start with, we want to define what a midsegment is. So a midsegment connects the midpoint of one side of a triangle to the midpoint of another side of a triangle. And each triangle is going to have 3 of these midsegments. Now what we want to start with is using GeoGebra. We're going to draw a triangle ABC. Once we've drawn our triangle, we're going to plot the midpoint of AB and the midpoint of BC, and we're going to draw that midsegment. So here I've started it for us. I drew triangle ABC, and I need to find the midpoint of AB and BC. So remember, we can use the GeoGebra to go ahead and find those midpoints for us. There's D and E, and then we can connect them using the segment tool, D to E, and we've got one of the midsegments of the triangle. Now, in this lesson, we want to then also look at how the slope and length of DE, that's our midsegment, compare with the slope and length of AC. So let's start by talking about, well, let's look at the lengths first, because those are on our picture for us. When we look here, you see that the length of DE is 5.02 and the length of AC is 10.05. And hopefully you notice there that 10.5 is just about double DE. Now remember, we talked in class that sometimes when we're using the software, we don't have the exact length, we have a rounded length. And so that's why we're not getting exactly double. But it's true that DE is half the size of AC. Now, if you look at the lines, you might be able to make a conjecture about the slopes and how you think they compare. Are they the same? Are they different? Are they opposites? Looking at them, we can tell that they're both negative slopes. But let's go ahead and calculate the slopes using the endpoint. So we're going to start out by finding the slope of AC, and we have that A is the point -2, 1, and C is the point A0. So we're going to come over here, and here's our 2 points. A was -2, 1, and C was 8, 0. So we know that to find slope, we do y minus y, so 0 minus 1 over x minus x. 8 minus -2, which gives us -1/10. So the slope of AC is -1/10. Next, we're going to do the slope of DE. DE's numbers aren't quite as pretty, but our slope formula works just the same. Y minus y, 2.85 minus 3.35. Divided by 4.78 minus a -0.22. And when we do this, we get -0.5 over 5, which if we simplify, we get -1/10. So you see that their slopes are the same. And what does that mean about the lines? Well, lines that have the same slope are parallel. Now I've gone ahead in GeoGebra and had it calculate the slope of DE and AC for us. You'll notice this in the middle where it has lowercase d equals -0.1, that's -1/10. And then down in the bottom right, it says E equals -0.1. And so they're both still -1/10, and it's telling us that. Now what I want to see is what happens when I move B around. If I move B, is my slope of DE changing? And it appears to be staying the very same. It continues to stay the same slope as AC, and since I'm not moving A and I'm not moving C, those slopes stay the same. So no matter where I move B, no matter what kind of a triangle this is, my midsegment is going to be parallel to that other side. Now, what happens if I move a different side of the triangle? What if I move A? Well, when I move A, you notice that those slopes did change. But what's interesting is now they're both 0.32. So the lines are still parallel, If I move it up here, now both of the slopes are negative 0.15. If I move C, the same thing happens. The slopes change, but the slope of DE and AC, they stay parallel. Now, is DE still half of AC? Well, AC is about 20 and DE is about 10. So without doing an actual calculation, it sure looks like it's still half as long. So what if I make it something like this? 6.5, 1, and if we double it, so it stays half the length and the slopes stay the same. Okay, when you get to this point, you've watched me create a triangle and draw the mid-segment and measure and do all that. Now what I'd like you to do is pause the video, and I want you to do these things. I want you to draw a triangle ABC. I want you to draw the mid-segments of all of them. And then I want you to find the lengths of each side of the triangle, the lengths of the mid-segments. Both of those GeoGebra will tell you. Now the only thing that you're going to need to do is you're going to need to find the slope of each side. Now I did use a little trick in GeoGebra. Down in the input, I typed slope with a capital S. That's a capital S. It matters in GeoGebra. And then it brought up a set of parentheses and it said line inside. You delete where it says line and you delete, it has these little symbols and it says line. So you delete that piece and you write the name of your line, whatever it is, lowercase a, lowercase f, and it will calculate those slopes for you if you want. You don't need to do that. You can just use the slope formula like we did, but take a minute here or a few minutes and play with the software and see if you come up with the same thing. Is your mid-segment half as long as the opposite side, and do they have the same slope? Okay, now that you've had an opportunity to play with GeoGebra and kind of looked at those, hopefully you were able to see what the mid-segment theorem said as well. Now we're going to look at this example. We have triangle JKL, and we have mid-segment M and N. And so we know M is the midpoint of JK, and N is the midpoint of KL. And we want to show that MN and JK are parallel, and then we want to show that MN is half as long as JL. So in order to find whether or not they're parallel, we need to find the slopes. So we're going to start by finding M and N, the midpoints of JK and KL. You remember, to find midpoints, you just average the endpoints. So we're going to add, for M, we're going to add -2 to -6 and divide by 2. Add 1 to 5 and divide by 2. And we get M is -4, -3. So we can write that on our picture, -4, -3. We're going to do the same thing for N. We add K and L's endpoints. So we add -2 to 2 and divide by 2, and 5 to 1 and divide by 2. Remember that you are essentially just adding the X values and dividing by 2, and then you're adding the Y values and dividing by 2. And we get 0, 2 for the endpoints of, or for the ordered pair for N. Now that we have those coordinates, we can go to find the slope. So we want to compare the slope of MN to JL. Well, the slope of MN we find by doing y minus y over x minus x. So we have 2 minus 3 over 0 minus a -4. Ooh, this was a +3 and I wrote it down as a -3. And we get the slope of MN is 1/4. And you could also tell that by doing rise over run. Rise 1, run 4. And we see it has a negative slope, so -1/4. Then we can find the slope of JL by doing the same thing, y minus y over x minus x. Remember, it's always the change in y on top and the change in x. So this is the change in y. This is the change in x. So it also has a slope of -1/4. So we know that since the slopes are the same, MN is parallel to JL. Now the last thing they wanted us to do was show that MN was half as long as JL. So in order to do that, we're going to need to find the lengths of both of those segments. So our step 3 is to compare the lengths. And we'll find the length of MN by doing the distance formula. We practiced the distance formula in one of our lessons the other day, where we subtract the x's and square it, subtract the y's and square it, and we add those together and take the square root. So we get the length of MN is the square root of 17. Now, since you have a picture up here, you could certainly go ahead and make a right triangle and do 1 squared plus 4 squared is 17, and do the square root of that if you want to use the Pythagorean theorem. Either way is fine. Then we need to find the length of JL. Again, by using the distance formula, we find that it's the square root of 68. If you simplify the square root of 68, you see that it's 2 times the square root of 17. Now, if you'd rather work with decimals, that's perfectly fine. You'll still see what's happening if you work with decimals. But eventually what we're getting is that since the square root of 17 is half of the square of 2 times the square root of 17, MN must be half of JL. So here we've proven that this works for yet another triangle. So here it says use the graph to show that the midsegment of DE is parallel to AC and that DE is equal to half of AC. So if you want to pause the video right here, this would be a great practice problem for you to go ahead and do. And then I'll put the answers up, but you pause right now and give it a try, and then come back and you can see if you were correct. So hopefully you saw that the slopes of DE and AC are both 3/2, so they are parallel, and that DE is the square root of 17, that's its length, and AC is 2 times the square root of 13. And so AC is obviously twice DE, which means DE is equal to half as much as AC. Now, on this second problem, it says find the coordinates of the endpoints of midsegment EF, which is opposite to AB. So AB is this side over here. We already have E, and so F must be the midpoint somewhere in this area, and we're wanting to draw this line and then see that it's parallel. Well, so in order to find that midsegment, we need the midpoint of AC. So we're going to do 5 plus 1 divided by 2, 0 plus -6 divided by 2. So F is positive 3, negative 3. That's going to be its ordered pair here. Then we wanted to show that it was parallel to BA. So we need to find the slope of EF and the slope of AB. Well, the slope here is up 1, 2, 3, 4, 5, and over 1. So it's a slope of -5. And then if we do the same thing here, we go up 10 and back 2. So -10 over 2 is also -5. So we see that those are also the same. And then we have the same calculation that we've been practicing where we find the lengths of both sides. So all of this is an exploration of this triangle midsegment theorem. And the triangle midsegment theorem tells us 2 important things. One is that the midsegment is parallel to the opposite side. So DE is parallel to AC. And then also the DE is half as long as AC. So if AC is X, DE would be half of X. Now this one is asking us to write a coordinate proof of the triangle midsegment theorem for one of the segments, and we're picking DE here. Now, if you look at our drawing, you'll notice what changed this from just being an example to actually being a coordinate proof. And that is, in order to prove something, we need to show it's true all the time, not that it's just true for the one triangle that we have drawn. So the big difference here, let's get a highlighter, is that when you look at our ordered pairs, they're no longer just numbers, they're variables. And so if we prove it works for these variables, we can prove it works all the time. So in order to start this, we're going to find the coordinates of D and E by finding the midpoint of 0B. So to find D, since it's a midpoint, we're going to do 2Q plus 0 divided by 2, and then 2R plus 0 divided by 2. And so we get the coordinates of D are 2Q divided by 2, which is Q, and 2R plus 0, 2R divided by 2, which is just R. So the coordinates for D are Q, comma, R. So every time we would use a number, now we're going to use these variables. Now for point E, we're going to use 2Q plus 2P, 2Q plus 2P divided by 2, and 2R plus 0 divided by 2. So that should go here. Now when you're looking at this, it looks kind of messy. We can't add 2Q to 2P, but we can divide both of them by 2. So we get whatever Q plus P is, that's the X value. And then 2R divided by 2 is just R. So E is the point Q plus P, comma, R. Now I know this does look ugly and it gets kind of messy because we're only dealing with the variables. But that's all right. We can work with variables. So let's start by finding the slope of DE, and we'll find the slope of OC, and we'll see if they're parallel. Well, to find slope, we do y minus y, so we have r minus r over x minus x, q plus p minus q. So we get 0 over this mess, which is actually equal to p, but it doesn't really matter because when we have 0 divided by p, or 0 divided by anything, we just get 0. That means what kind of a line is DE? Well, it's a horizontal line. And what do we see about OC? Well, it's also a horizontal line because we're going to do 0 minus 0 over 2p minus 0. And we can also tell, so we get 0 again, it's lying on the x-axis, so it must be a horizontal line with a slope of 0. So we've proven that those slopes are going to be parallel, not just for this one, but for all triangles. Even if we were to turn it sideways and have different slopes, they would still be the same. The next thing we want to do is find the length. Well, the nice thing about finding the length of a horizontal line is you just need to subtract the x's. So the length of DE is going to be Q plus P, because that's obviously the larger, it's further to the right, minus Q equals P. So DE has a length of P. OC, our y values are 2P, our x values are 2P and 0, so it has a length of 2P. So the question is P equal to half of 2P? And it is. So we've proven both that the lines are parallel and that DE is half of OC. Here it's asking us to find the coordinates of F, the midpoint of OC, and then repeat the process for those. And it would be a little messier, but if you want to go in and practice with that, you certainly can. We're going to skip past that and look at this one more example. It says triangles are used for the strength in roof trusses. In the diagram, UV and VW, so here's UV and here's VW, are mid-segments for RST. Find UV and RS. So we know, if we just look at this one, we're looking at the big triangle that we want to have our eye on is this one. If that's the midsegment, then it's half as long as RT. So if RT is 90, UV must be 45. Then if we look at this one, if this is 57, they ask us to find RS. That's the outside. It must be twice as long. So RS is going to be twice as long as 57, which is 114. And those are both in inches. So that's how we can use the midsegment to find pieces of other triangles.